Hello folks, and welcome back to Physics with Captain Rod. The purpose of this video here is to just give a demonstration on how to use angular momentum for problems involving impacts. So what we're looking at here, we've got this bar hanging here vertically, and I've got some data written over to the right here. This m sub b is going to represent the mass of that bar, 5 kilograms. And this bar has a length written to the right over there of 2 meters. And we're going to imagine that this bar is going to be struck by this chunk of putty or something like that. And the chunk of that putty here, I've got 2 kilograms for the mass. And that putty is moving at 10 meters per second at the instant shown, or at the instant it hits that bar. We're going to imagine that it hits the bar basically right there, dead center, and sticks to the bar. Now, if the putty sticks to the bar, if we think about how it's going to behave, the bar now, if it's hinged and free to rotate about this axis, will do so. And then what it should do is it should rotate up to some sort of angle. And what we're going to try to calculate is that angle, theta. We're going to look for the maximum angular rotation. Now, something to consider before we even get working on this problem, if this thing had a high enough kinetic energy, this putty, it's conceivable that even after impact, the system has enough kinetic energy to go all the way around. So conceivably, theta max, it might be 180 degrees. I don't know. And I'll try to demonstrate, or try to point out how we would know that as we work the equations. Okay, so I'm going to call this picture 1. And this putty then is going to hit this bar, and it's important to realize that what's going to happen now is the bar is going to be rotating. So I need another picture just after rotation. So what I'm going to do here is I'm going to clone this bar. Actually, I'm going to clone the whole thing here. Oops. Do that again. So I'm going to draw a second picture, call it picture 2. All right, except that in picture 2, this putty is now stuck to the bar, so basically it's right here, and let me get it looking as close, get it looking as close as I can to what I had in the first picture. And this system is now rotating. So here's my picture 2. Oops. And we have now a rotation in this direction, which I'm going to call omega 2. It's an angular velocity. It's in picture 2. Okay. Now my picture 3, I'll just freehand this one. This bar is now rotated up to some angle, theta. And here's our putty mass. So, and I'm not going to take the time to pretty that one up. So, important things to be able to do here. You have to recognize that there's 3 important time frames. Here's an instant in time before impact. This is an instant right here just after impact. And this is after this thing has rotated up to position 3. Now, I'm assuming here that this theta is less than 90 degrees here, but our work actually is going to be good from theta equals 0 all the way to 180. Right? Now, another important thing is recognizing what type of math or what type of concepts to apply. This is an impact, so momentum should hopefully be the first thing we want to consider. Translational momentum, however, is not conserved in this problem, and the reason is this. When that putty hits this object here, that's going to give an impulse here at the pin. That impulse will have both an x and y component. So that's going to change the net momentum of the system horizontally and vertically. You can see it in the pictures pretty easily if you consider this. Picture 1, if I define my system as all of this, picture 1 has a momentum in the y direction that's positive. However, picture 2 doesn't. At the instant shown, everything has just horizontal velocity components. So you can see quite easily that translational momentum is not conserved. What is conserved, however, is angular momentum. And the reason angular momentum is conserved is because in order to change your angular momentum, you need a torque or moment. And if we look at all the forces acting on this system, particularly the one at the pin, that force at the pin might be something like this. I might call it something like px for pin force, x direction. There's probably a py. There's also a gravitational force, mg. Those are pretty well all the forces acting on the system that I can think of. None of them create any torque or moment about that point. That's why the angular momentum is conserved in this problem when the linear or translational momentum is not. So there is an external force or impulse that would change your linear momentum, but there's no external torque or external moment to change your angular momentum. So I'm going to go ahead and write conservation of angular momentum from 1 to 2, except I'll do that in a better color here. So 1 to 2, conservation of L, meaning angular momentum. Now, when I look at picture 1, we have a linear momentum equal to mv for the putty. Now this velocity 1 here, let's see, makes a 30-degree angle with the horizontal. It's important to recognize here that, and especially you have to consider this right before it hits the putty here, or right before it hits the bar, the vertical velocity component of the momentum basically goes right through the pin, or pretty darn close to it. So that thing does not create any angular momentum about the pin. The x component of this thing's velocity does. So the angular momentum in picture 1 about the pin is going to equal mass of the putty times velocity putty picture 1 times cosine 30 degrees. That's going to give us the x component of this guy's momentum, and then I'm just going to multiply that by L over 2. Right? So mv cosine 30 is the component of the linear momentum that's to the right, and then times L over 2 here, because when we project this vector to this point, this is going to be right before impact. L over 2 is going to be distance to the axis of rotation. So this quantity gives the net momentum, the net angular momentum about the pin. And that quantity is positive because generally speaking, I'm doing counterclockwise positive for the rotational vector. Right? Now what I'm going to do is talk about the net angular momentum in picture 2. Now, picture 2, this is a rotating body, and I'm just going to put this on the upper right. The easiest way to write out the momentum of a rotating body is I omega, where I is the moment of inertia, omega is the angular speed. So what I'm going to do here is I'm just going to write I times omega 2 for the angular momentum that we have in picture 2. Now the I, there's a couple things going on. We have both the bar and the putty. I'm going to take them one at a time. As far as the bar is concerned, this thing is rotating about the end, so we can write its angular momentum as 1/3 ml squared, where that m is the mass of the bar. I'll put a little b on there. Plus, now the moment of inertia of the putty about this axis, and I'm just going to treat this basically like mass about a point. So that's going to equal mass of the putty. I need a little more room here. Times this distance squared, which is going to be L over 2 in this example. So that's going to be, I'll just put L squared over 4. That's going to be mass of the putty times distance squared, and the distance is L over 2. Then times omega 2. So here is the moment of inertia of this system about this point. You notice that I did not include a rotational term for the putty. That's because the moment of inertia of this object about its own centroidal axis is definitely going to be very small compared to the ml over 2 squared term. Right? And now, here's the million-dollar question. Are these equal? And the answer is yes. And the reason, in order to change your angular momentum, you have to have a net torque or a net moment. All right? There's no net moment on this system. I already discussed why earlier in the video. So these are all numbers that are given in the problem. I'm going to take a moment now, and I got some helpers here, and I'm going to have them calculate values. So if you guys would you please run every number you see here, divide by every number you see here, give me an omega 2. I think what I'll do here is maybe just pause this for a second while my helpers calculate that. Okay, so we have my helpers. They all agree that when they solve for omega 2, they got 2 radian per second. So now we know the rotation rate in picture 2. All right, so now we're going to think about what's happening from 2 to 3. Well, you'll notice we've got a kinetic energy in picture 2, but not in picture 3. When this is at its maximum value of theta, in theory, this thing is saying is still. Now, I said in theory, and I'll explain why here once we get our equation written out. So I'm going to go ahead and write out the work energy theorem for this. I need a little room here, so I guess I'll do this up here. So PE2 plus KE2 plus work equals PE3 plus KE3. And again, we're assuming that there's no KE3. All right, PE2. So now we got to define a datum. I like to, for rotational problems, put my datums right through the pins. So our PE2 term has 2 terms, one for the bar, one for the putty. So I'm going to put minus mass of the putty G times L over 2. For the bar, we're going to have minus mass of the bar times G times L over 2. Right. Kinetic energy terms. We can get that done with one term if we do the moment of inertia, total moment of inertia about the pin. So I'm going to write that 1/2 I. Now we already have a value for I. I'm going to go ahead and put this in 1/3 m sub b L squared plus mass of the putty times L squared over 4. That's the moment of inertia of this system about this point. Right? And then times omega 2 squared. There's our kinetic energy term. I guess I'm out of room, so I'll just start out new line. Equals. So again, let me make sure that this is easy to follow. So we're saying that all of this, right, is equal to, now I'm looking at picture 3. Potential energy in picture 3, there's going to be 2 terms. We're going to have minus mass of the putty, G times L over 2 cosine theta, where that cosine theta is an unknown. The L over 2 cosine theta is coming from this distance right there. We also have the bar, so we're going to have a minus m mass of the bar G times L over 2 cosine theta. There's our potential energy of the bar. I'm going to assume that thing is not rotating. I'll talk about that assumption here in just a moment. I want to go back and talk about the work term and why we didn't have a term there. So we've got forces acting on the pin, but there's no displacement, so there's no work term for that. Then we got gravitational forces, which are doing work from 2 to 3, but we've got those taken into account with potential energies. So this is kind of a long equation. We've got this green equals, I'll just put this thing in red. Now, this 0 assumption here, we're going to find out if this is valid or not. If we get an answer here between 0 and $180 or 180 degrees, we're going to be done with this problem. If we're between 0 and 90, it means that this bar made it up into this quadrant here, which I generally would call it quadrant 4. If we get something between 90 and 180, it means that this bar made it up here into quadrant 1. And if we get no solution to this, that means there's got to be a term here, which means the bar gets all the way around and has a kinetic energy at its highest point. So I'm going to pause this while I wait for my helpers to find me a solution to this. Okay, helpers. Okay, folks, I'm back here, and my helpers are all concurring that this seems to have a solution of theta equals about 42 degrees. I'll just put theta equals approximately 42 degrees. So let me just kind of overview the highlights of this problem, at least conceptually. Very important to recognize why it's angular momentum that's conserved, because when this putty hits this block, there is going to be an external impulse on this system applied at the pin. So linear momentum, not conserved. Angular momentum is, because that pin force is not going to produce any torque or moment about this point. So 1 to 2 is an angular momentum conservation. And then 2 to 3 is just a standard work energy theorem. Total energy system picture 2 equals total energy of the system picture 3. I hope this video helps demonstrate these concepts. Have a great day.